All right, we're going to wrap up our work with compound probability with this video here on conditional probability, and we'll start with an introduction and do some examples as well. Conditional probability is written like so, and we read it like this: probability of A given B. That little line right here is a vertical line. It's not a slash. There's a vertical line on your computer keyboard if you look for it, and we read that as given. Okay, so probability of A given B. And what that really means is if we know that B has already happened, so B is the given thing, if we know that sort of extra information that B has happened or is true, what's the probability now of A happening? Okay, so sometimes A and B are related or connected, and if we just look at the probability of A without knowing anything about B, that will probably be different than the probability of A given B. So if we know that B has already happened, what's the chance that A is going to happen? So a couple examples. I roll a die, and it's given that it's even. Okay, what's the probability of it being a 2? Well, that's going to be different than just the probability of it being 2, right? Once we know that it's even, the chance of it being a 2 increases, even though we've already rolled the die. Okay, so we're just getting some extra information which helps us adjust our probabilities. Next one, we draw one card out of a deck, so just one card. It's given that it's a queen, so you kind of already know most of what the card is. Well, you don't know the suit, but you know it's a queen. What's the chance that it's a king? Well, that's impossible, right? So that would be a probability of 0. And that would be very different from asking about just what the probability is that it's a king. Okay? There's a formula as well, and I don't honestly use this formula very much. I'd rather kind of think through each problem and solve each problem on its own. But the formula absolutely works, especially if you're stuck, if you're in a pinch. You can use the formula. So the probability of A given B is the probability of both of them happening divided by the probability of B happening. Okay? Venn diagram style, real quick, let's say this is A and this is B, and you're wondering, first off, let's say you're wondering just what the probability of A is. That's going to be this. Okay? But now, let's say we are given that B has happened, and we can zoom in on this probability of A out of the red circle, okay? So we can then start ignoring all this stuff that says B didn't happen, and we're now just focusing on the B circle, okay? So this is A and B, and the whole red circle is B. So that kind of, in terms of color coordinating here, probability of A and B divided by the red circle, which is just the probability of B. Okay, so we're eliminating a whole chunk of our possibilities, and that allows us to change our final answer. So let's look at some numbers or some examples. Okay, rolling a single die, the probability of 3 given that it's odd. All right, and what I want to do here is, I think it's easiest to just write out the possibilities. And I'm going to copy these down for the next possibilities as well. Okay, for the next questions. All right, so let's look at this first one. Probability of 3 given that it's odd. So I'll try to write what we already know in green. So we know it's one of, not 6. 6 isn't odd. So we know it's one of those. So what's the chance that it's a 3? It's 1 out of 3. Okay, so there are 3 possibilities, 3 odd numbers, and one of those is the 3 we're looking at. Next one, probability of odd given that it's 3. So that's given, that 3 is given. What's the chance now that it's odd? Well, it's 100%. It's guaranteed. It's like rolling a die and saying, hey, I just rolled a 3. Now you tell me what's the chance that that's odd. Well, of course it's odd. It's guaranteed to be odd, right? Next one, what's the chance of getting a 4 given that it's odd? So highlight my odds. How many of those are 4s? None of them are. So we have a 0% chance, or 0 out of 3, or 0%. Last one on this set, probability of 2, given that it's less than or equal to 5. So those are our numbers less than or equal to 5. Okay, and how many of those are 2s? One of them is a 2 out of 5 possibilities, so 20% or 1/5. This idea of conditional probability works really, really well with tables. And let's go, I have, I think, 3 different examples for tables, and we'll try to get through them relatively quickly. So here we have categories of men, women, and handedness. And so we have a sample of 1,000 people, so that's our grand total right there. And I like to check off or cross off numbers as I use them. 500 are men. That means that 500 are going to be women, and this is all assuming gender binariness. Okay, I know gender is much more complex than this, but we're trying to keep it simple for this particular example. 63 of the men are left-handed, so I took that into account. And let's find the right-handed men right now. 500 minus 63 is 437. There are 887 total right-handers. Okay, so we can find everything else from here. So 887 minus 437 is 450. These numbers have to add up to the 500. So this is a 50. And 63 plus 50 is 113. And we can always check, do these add up to 1,000? And they do. Okay. Probability of men and left-handedness, that's a 63 out of 1,000. All these numbers, most of these are probably going to be out of 1,000 until we get to some conditional stuff. Probability of women or left-handedness. So these are all our women, and these are all our left-handedness. Okay, so let's use our formula. 500 women out of 1,000 plus 113 left-handers, and then minus the 50 that we're counting twice. Okay, so that's going to equal 563. Probability of women given left-handed. Okay, so I'm going to try to highlight this in a particular way. We know that we're dealing with left-handers, so we don't need to deal with any of these numbers. I'm going to cross them off. Don't cross them off on your paper because it's easy for me to erase them here, okay? So this is all going to be out of 113. How many of them are women? 50, okay? So you're really just only focusing on the left-handers. Probability of not being a left-hander? Well, that means you're right-handed, right? So that's 887 out of 1,000. And then probability of being a woman is 1/2, 500 out of 1,000. All right. Sometimes the challenge is actually filling in the data table. And so let's do that one right now. And so here I'm giving you only a portion of the numbers. I don't have any sort of an introduction or any other information available. And we just want to make sure everything adds up. So these things have to add up to 102. So that is going to be a 50 right here. What happened? Okay. Let's see. So that's going to be a 50. These numbers have to add up to 102. So that's going to be a 30. These numbers have to add up to 52, so that's a 19. And then just keep going like that. 72 minus 33 is a 39. Let's get this by doing 50 minus 39. And that's an 11. And then we can always check by making sure these add up to 30, and they do. Okay. Looks like we have some IQ numbers and whether or not they have a particular gene present. So we have to try to figure out what this shorthand means. H given P, I'm going to assume that H represents high IQ and P represents gene present. Okay, so sometimes either ask if it's confusing, ask your teacher, but sometimes you can just kind of figure out what the shorthand means. So out of all the people that have the gene present, which is 72, how many of those 72 people have a high IQ, and that's 33. Okay, so again, we're crossing out all these people that don't have the gene present. Okay, next one, typical IQ given present. So again, it's going to be out of 72 and 39 out of 72. Okay, so again, we're only dealing with the gene present portion of the population. And then probability of A, I'm assuming A means gene absent, so there's no conditional probability here. We just look at the total, 30 out of 102. All right, moving on, one last one. This is a survey of college students. You probably saw this in the Venn diagram video we just did, but you can do this with a table as well. Okay, so let's fill those guys in. 56% of students live in the dorms. So that's right here. And let's say it adds up to 100. So that means this has to be 44. 62% are on the meal plan. So that goes right here. Come on. Try to get this back down. Okay. Okay, cool. 62% are on the meal plan, which means we have a 38 right there. Okay, and we can check off that piece of information. And then 42% do both. So where's dorm and meal plan? That's 42 right there. Everything's got to add up, so let's go ahead and do it. This has to be a 14, this has to be a 20, and this has to be a 24. Okay, so the numbers that I think you saw in the Venn diagram were these numbers, okay? Just the most sort of split up individual categories. But here we actually have a little bit more information, so in some ways the table's a little bit easier to work with. So dorm and meal plan is going to be 0.42 or 42%. Chance of not being on the meal plan is this 38%. Probability of the dorm or the meal plan. So remember here we could use our formula. 62 is the meal plan plus 56 for the dorm minus 42 both, and that's 76%. And then not that, which is the complement, is going to be 24%. All right, so maybe you can think for yourself about which one's easier to use. Is it the Venn diagram or is it the table? Which one do you like better? That's a good place to stop.